So welcome back, folks. We're just running the clock. Currently, we have a representative for the in-person section, and we have a representative for the online Zoom section. So we definitely have a quorum to get going. Any questions at the moment, folks? Hey, this is even better. Now we have a tie. So two people in person, two people in Zoom. This will be a great class. We'll make this one work. By the way, this is usually the lowest attending class for the entire academic year. Even the one before Thanksgiving break, it has a higher attendance. But there's something about spring break. I think we're just tired. We're in the second semester. And so this is a really hard class to attend. Appreciate everyone making it. And if you didn't make it today, you tend to watch the lecture later in the recording. I totally understand. I missed a lot of these classes as well as a student. But for the announcements so far, I haven't been able to start the grading just yet. I'm still waiting to get the rest of the exams back from the Pocatello Testing Center. Once I have the full set, I'll begin on the grading, and I've planned to have it graded at some point over the weekend, possibly on Sunday if I'm running a little bit behind. If I run super behind and it gets into spring break, that's a possibility, then it'll be graded on the 31st, or excuse me, the 24th at the very, very latest, because I want to break too. I don't want to leave stuff for the rest of the week. So I'll try to get these graded as soon as possible. If you took the exam in the online testing center, I'll just be emailing back your exam. If you took it in person and you're super curious about your grade, don't hesitate to email. I'll be happy to give it a scan and send it right back to you. So that's what's going on with the exam information, or that's what I have here. Once we're done with the grading, I replace this with just basic summary statistics so you can see how the class did as a whole. Then going forward, we're just about to finish section 3.7, just a little bit extra work on derivatives. And then we'll turn over to chapter 4. Actually, this sounds kind of rough starting a chapter across spring break, but this is a good one to start because 4.1 is kind of a lighter topic. It's applications of the derivative. 4.2 is the hard one. That would have been a bad one to start today. And then 4.4 is when we put it all together and start doing actual applied problems with real context, that kind of stuff. So 4.1 is just building towards that objective. And with the rest of my announcements, I guess we have spring break coming up, and that's a nice one. If you're in a position where spring break is more of a catch-up week for you, I apologize about that, and I understand that it's kind of how it is for me a lot of times. If it is a catch-up week and you're working, don't hesitate to send me an email at any point. If you're in the WebAssign system, click the Ask My Instructor button the moment a question comes up, and I'll be happy to help out. I'm not on my computer all the time during spring break, but what this comment is really saying is I do check my work email every day of the year. It just makes me feel weird if I don't check it. I check it in the morning, so whatever messages you send me, and it can be a lot, I'll just get to them on the morning and reply back to you in a systematic way. So that's the plan so far, folks. Any questions at all before we get started? Okay, let's take a look at what we left off on. Back in section 3.7, we left on this one. This is kind of a rough one to come back to after a weekend and exam date. So this was a week away from today. Let's break down what we did. This problem was all about properties of logarithms. And I also mentioned here as just a side comment, there'll be a similar question to this one on the real exam 3. So I propose we do a second version after we finish this one off, just as a full reminder on how this goes and extra practice if it's really going to be an exam question, which it will if I say that. Usually that's kind of a dead giveaway. So what we want to do in this problem is differentiate t of x. But there are so many rules of differentiation just to get through this one. It's a chain rule with the logarithm, which is already complicated, which becomes a quotient rule due to that fraction bar. And in the quotient rule, you'll have a product rule from here, a chain rule from here, another chain rule from here. It's just a really, really complicated problem to attack directly. Using properties of logarithms, they intersect really, really nicely in calculus because you can start breaking down a really compact structure like this and essentially spread it out into individual components. That's not hard to differentiate. Neither is that part. It's a little bit harder. It's a chain rule. This is a chain rule exactly like before. So what we're doing is taking something that involves lots of properties simultaneously and just applying them one at a time on each one of the individual terms. The complexity down here is way, way lower than the original problem. Any questions at all about the expansion of the logarithms before we go to differentiate? Okay, let's do the work of actually differentiating this then on the next step. And some of the derivatives are a little bit faster than the others, though the one in the middle, the one on the far right are the slightly harder ones. So let's analyze these carefully. Taking the derivative of that part by the red dot is a chain rule, and this would be the inner part. Same with this one. Then next, the log base 5 is going to be the outer part. And same with that log base 5. And maybe last thing we should put down on paper just as a reminder is that the derivative with respect to x, I don't think I have enough space for that. Let me put it somewhere where we can see it a little bit better. The derivative with respect to x of log base b of x becomes 1 over x, multiplying that extra corrective factor. This is the part that's easy to miss. We take the natural log of b. So that's the structure of the derivative that comes into play where we do derivative 1 outer on this one and on this one. B is playing the role of 5, so we'll have natural log 5 down there. Now we're ready to get started. The derivative of t at x, first we use the constant multiple rule. This will be 3 times 1 over. The rule over here on the right in purple says derivative of log base 5 of x is just 1 over x multiplied by the natural log of that base. So one term down, now we're a third of the way done. On this one, same rule to start. 1/5 is multiplying, so constant multiple rule first. 1/5 times. Now it's an actual chain rule, so we should be pretty careful with this one. When we follow the process, the one says do this derivative first, meaning we're differentiating log base 5. Where x is, we just blow open a placeholder like that, and then include natural log b over here. Then coming back to this part, the inner function 7x minus 8 informs us that 7x minus 8 will go down here, and that we must multiply by the derivative of 7x minus 8. So this one we'll do in one extra step to finish it off entirely, but this is a good start. The last derivative indicated here is just putting a 7 in the numerator, so it's basically done as we look at it. Any questions with this one at the moment? That's so far the harder derivative out of that long list. Okay, if the structure of how this one got differentiated makes sense, we're essentially doing the same thing on this one. So let's see if we can compare both and see the parallelism. First, the constant multiple rule gives us a -4. And just so that's not a distraction, let me kind of put a border there. So -4, we do the derivative of the logarithm, which causes a fraction to occur, with natural log 5 attached in the denominator of that fraction. Then we multiply by the derivative of one extra thing. So just like before, the inner function, x power 5 plus 3, goes into this denominator, totally unadulterated, just copy it in. Over here, it's not unadulterated, that's a double negative. We have to differentiate it, so don't forget to put the prime symbol on there each time you're doing a chain rule process like this, just as a reminder. So 2 chain rules down, we just need to finalize these 2 derivatives and kind of simplify as we go. So our end answer on this full process is that the derivative of t at x, t prime of x, is equal to, left to right, we have 3 over x natural log 5. Plus, on this one, I would probably bring the 5 together in the denominator. 5 7x minus 8. Natural log 5. I do see a typo on here. I think I know what I was thinking when I wrote that b. I think I was looking at that formula. That's literally where my eyes were. We have to fill that in, right? B was supposed to be a 5. So let's make a correction right here, right now. Little arrow to signify that correction. Don't forget that 5 actually goes there, not a b. Then the derivative of this is just a 7. It's multiplying the fraction, so it just gets pushed into the numerator. And that term is now done. One more to go. We'll leave the minus parked in the middle between the fractions. This 4 goes into the numerator, but then it's also multiplied by 5 times x power 4. That gives us a total of 20 x power 4. So that solidifies what's happening in the numerator. Then down below, just copying, we've got x power 5 plus 3 times the natural log of 5. That's a lot to type in when you're giving this kind of an answer in the WebAssign system. As far as the parentheses go, if you have it written this way, you don't need any extra kind of clarity. But if you're putting this into WebAssign and you type it in this way, this would actually be a huge problem. WebAssign can't tell the difference of x as an input to the natural log and multiplying natural log 5. So if you put the natural log 5 to the left, you really are required to now put parentheses around that 5 to say x is multiplying the result of natural log 5. This is not meant to be a function of x. Usually I just keep it to the right, where if it is towards the right, it's less of a critical issue of what's going inside the natural log function. But any last questions, folks, going through this one? Okay, kind of a tough problem to come back to again after a weekend and an exam day. So I propose, because it's an important problem, it'll be on exam 3. Let's do the whole thing all over again. I'll just make up a random problem like this one. We'll use properties of logarithms again to break it down. Then we'll differentiate a result. So let's just call this example 3. Version 2. That would start off as a real exam question by saying, use properties of logarithms to fully expand the function. This would be the part A to the question. Part B to the question would be to differentiate your result in part A. So generically, that's about how the whole question would be written. The properties of logarithms wouldn't be on the problem itself, but I'm thinking about including that as part of the exam 3 formula sheet, since if we've observed in this kind of problem, it's critical to have those and be ready to work with them. So let's let our function be f of x equals, let's do a natural log on this one. We suffered through a log base 5, so we could treat ourselves to the natural log. Bunch of stuff going in it, so we'll organize this way. And let's let this be x cubed. How about square root 5x minus 8? Down below, let's also go, there's lots of interesting things we could do. Let's make this be e to the power 5x. Let's add another factor in the denominator of, how about 7 power x? So I don't know if that'd be a great exam question necessarily, but roughly it's pretty similar to the one that we did above. As we'll solve it, we'll see how complicated it gets. It looks like it would probably make a pretty good one. So to start off, we'll use properties of logarithms. The particular ones that we use the most in this context are properties 5, 6, and 7. But also, you can make a surprise use of either property 1 or 2. Usually in this context, it's more likely property 1 because the logarithm is on the outside. versus on property 2, the logarithm is on the inside in the exponent position. So these are the ones that you're most likely to be using, but all of the properties are actually important. So some of these could also potentially be used as well. Going just in stages, I would probably begin by using property number 6 first. Break up the quotient. If you're really good at this, some people can just write it down as one step, but when you're learning it or just refreshing your knowledge on this, being methodical is a great idea. So step 1, because of that fraction bar right there, we'll use property number 6 to start. F of x is now equal to natural logarithm x cubed times, we want to make a correction on anything that has radical notation, whether it's a square root, fifth root, anything like that. On this one, the correction would be 5x minus 8 to power 1/2. The 1/2 coming from that being a square root up here. Now, property number 6 is finally actually being used once we go minus. So there's the property number 6 action, the natural log of e to the power 5x times 7 to the power of x. So now we're on our way with this. That minus is kind of a pesky thing to have right there, and we'll see why in just a moment. It might be a good idea just for extra safety algebraically to put a bracket right there after that minus. So we did the quotient rule for logarithms. Now, those multiplication symbols are not necessarily written in. Notice in the numerator it wasn't. It was written in the denominator just for the sake of clarity. But if you'd like, it's good to enforce that multiplication symbol here and here, because it's a really strong reminder you're doing property number 5 on the next one. So property number 5 happens right here and right here. Let me fix my notation on that. Any questions so far to this stage? Okay, we've expanded a little bit through property 6. This is still a really tough problem. Property number 5 makes it become more manageable. Notice we're only writing f of x because all we're doing is using properties of logarithms. This is not a derivative. It's just a nicer way to write the function. So property 5 says additions can result whenever we have a multiplication here. The logarithm of a product is just the sum of the logarithms individually, is what this is saying. So we have natural log x cubed plus natural log 5x minus 8. And let me format that slightly better with a bracket. 5x minus 8 with a power 1/2 on it. So here's one result through that property number 5, a plus in the middle. And now this explains next on this step why we have a negative sign there. When we use property number 5 again over here, we're going to get 2 more logarithms, but that negative sign will distribute through the whole group right here, flipping them both to negative signs. So it's now natural log e power 5x plus natural log 7 to the power of x, and we'll distribute the negative sign in on our next run. But this plus right here, that's the property number 5 actually being executed. So we use properties 5 and 6, but property number 7, this is the major one. And when this is ran as a real exam question, it's also the one that's easiest to forget, which is kind of unfortunate because forgetting property number 7, the fact that you can move the exponent down, means this is still a really, really tough question. So let's make this a big deal as a reminder. This is still a hard derivative. Don't forget property 7. So property 7 is here to actually make this a really approachable problem. So starting to run out of ways to indicate these properties. Let me switch to this color here. So for property number 7, we'll be adjusting the exponent here, 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 and here. Notice it affects essentially every single term in the problem. So forgetting about it is, again, not really going to make the problem very approachable, even on an exam. It still is tough at this stage. So property number 6, or excuse me, number 7, signified here. I don't want to draw too many arrows. It gets hard to look at after a while, but it looks like this next. F of x is equal to power 3. Let's take a look at the property where it's written as a power p. P comes down as an exponent, and that is major with logarithms. It means this exponent, power 3 on x, can now be regarded as a coefficient. 3 natural log x now on that one. I'll just box out the parts that moved through property number 7, so we don't have too many arrows everywhere. Plus, here, 1/2 moves down, same property. And we have natural log 5x minus 8. We're stuck on these. So one thing that's really important about properties of logarithms is we have to know when we have properties, when we can break things down. And we also have to know when we're stuck. These properties don't really convey that as well. So let's say it here as well. Natural log of a plus or minus b, doesn't matter what sign you have in the middle, it's not equal to, make sure you kind of emphasize the not equal if you write this down, natural log a plus or minus natural log b. Doesn't matter if it's a log base 3 or the natural log, same property. So that means when you get to something like this, multiple terms inside the logarithm, but not multiplied, we're stuck on that one. That's as expanded as this term can get. But let's keep on going. I want to do 2 things on this one. Negative sign is going to distribute down, or excuse me, distribute through, and then the exponents will come down. So this will start off with a negative 5x, natural log of e, and then last one, right over here, this is going to flip to negative as well. At the same time, x comes down, and we just get natural log 7. I'm highlighting the negative sign in yellow because it's really disheartening to get everything right, but forget that negative sign. It's pretty subtle that when we had a group like this, the negative sign will distribute through. So watch out for that little action there with the negative signs. We're not quite fully simplified, but this is really pretty close. Any questions at all, folks, using property 7? Okay, let's look at this really carefully. There is one property, either 1, 2, 3, or 4, that we have not used, that we can still use. If we can find that property, when we go to take this derivative, it's even easier. Anyone see the one part of this last line somewhere between here and here where one property is still on the table for us? One of these 4 highlighted in yellow. Property number 2, let's see here. B to a power log base bx is x. You're really close, but we don't have anything to a power of a logarithm so far in this expression down below, but you're very close on property 2. Kind of tough to see, right? Let me give an extra hint to this. Kind of the point of this kind of problem is really just to study properties of logarithms themselves. It's kind of a big refresher at the same time of doing the calculus. The one that we needed is actually property number 3, but it's really hard to spot, right? There's a property 3 somewhere inside here. Reason it's hard to spot is property 3 is written in a generic way. It has a generic base b, and the input is b itself. That means it's not well tuned to our problem, which is a natural logarithm. So let's just rewrite that. If we rewrote property number 3 as a natural logarithm property, it would look like this. Log base e of e equals 1, or simplified even further, once that completes, there we go. Log base e is just another way to say the natural logarithm. Natural log e equals 1. So if natural log e ever comes up, there it is. It's a cancellation. That's just 1, so it's just gone from the problem. In fact, you might have canceled it right here. That's what we did in the section 3.6, dealing with exponential growth and decay, where we had e to the power of k times t, and we're solving for k or t. We took the natural log of both sides because that's a cancellation. Or we could do cancellation after the properties of logarithms. It'd be the same exact result. So this cancellation here is through property 3. We can't do anything with that one, sadly, but canceling that does reduce the complexity of the entire problem, so it was worth it. This is where our answer ends. The fully expanded function is f of x equals 3 natural log x plus a half of natural log 5x minus 8. And then notice how easy this derivative got. This is just a minus 5x. That will take us essentially no time to compute. That's a derivative of -5 and done. This one, however, by the red dot, is a majorly tricky derivative sometimes. Let's rewrite it in a way that feels familiar. If you're differentiating something to x power 1, to help your mind out, you want the coefficient in front because it just organizes what's the next step. Natural log 7 is part of the coefficient. It's a constant because there's no x there. So let's rewrite this entire term as negative natural log 7 times x, with the extra information that this one is constant. So we have a fully expanded form. That means on part B, all the difficulty has been sidelined over here, far less difficulty than differentiating outright at the beginning. And now the derivative is the easiest part of all this at this point. So we'll do that next down below, f prime of x. Well, that's our review of properties of logarithms essentially through these two big problems. Next derivatives are going to go like this. Just as a reminder, this time we're differentiating the nice version, not log base b of x. Derivative with respect to x of the natural log of x is just 1 over x. So great property to have. That means over here, when we go to differentiate, this is 3 times 1 over x, or just simply 3 over x on that one. Next one requires a little bit of caution, so let's do just that. There's an inner function, 5x minus 8. There's an outer function, natural log x. And there's a constant in front of all that, so we'll use the constant multiple rule as well and go plus 1/2 times. That's the constant multiple rule. Derivative of natural log goes like this. Then grab the inner function, put it in those last positions, 5x minus 8 here, and here where it gets differentiated. This one is a standard derivative. Derivative of -5x becomes -5. And this one is majorly tricky. It could be thought of as by analogy. When we said the derivative of this one was just -5, that's because -5 is coefficient and x is to power 1. X is also to power 1 right here. The coefficient is negative natural log 7. So by that same exact pattern, from this term, you just go minus natural log 7. I think that's really kind of hard to see. Does that make sense to folks on taking this derivative and coming down to that result? Yeah, absolutely. One way to think about it is our derivative for that last piece right here, negative natural log 7x, well, it also involved x way out here. Here's another way to think about it. You could say if y equals negative 5x minus natural log 7 of x, that means y is also equal to negative 5 minus natural log 7 times x. So we could just factor x to the full far right if we really wanted to. Nobody's going to stop us. The thing in the middle is complicated to even look at though, right? It's a bunch of stuff, but the fundamental thing is that it's constant. So when we go to differentiate y prime, power rule says x is to power 1, so it just becomes 1 times whatever that is, no matter how convoluted it becomes. We just get negative 5 minus natural log 7 times 1. New power on x goes to 0, so now it's just completely gone from the problem. And this is our result, y prime, negative 5 minus natural log 7, which is exactly that component right there, negative 5 minus natural log 7. So even though it's kind of done in a roundabout way, factor out x, the thought is it conveys that this is just a constant, it should come down. And this being just a constant should track coming down exactly in the same way. But does it help to visualize it from that point of view?
You were just doing the derivative of negative natural log 7e by itself. It would be negative 1/7.
Well, this one as a derivative just by itself would be y prime is 0, because now it's the constant rule itself. Up here, it was the constant multiple rule, as same as over here. But if you have just no x apparent, derivative will be 0, much like if, say, y was equal to 10, we would just say y prime 0 altogether. It just feels different, right? The moment you put in abstract looking coefficients, our pattern recognition behaviors in our mind just gets really, really thrown off. So part of our goal here is just to train our eyes to see it. If it's a constant, derivative should just be the negative natural log 7 coming way down. Or another way to think about it is, if it looked like that, that would have been the result. If it was just negative 7 times x, derivative of that is, well, just negative 7. Bring back the extra complexity. Now it feels way different, right? But it plays the same exact role. It's just a constant. So differentiation on times x power 1 gives you exactly that constant coming down. But other questions or comments, folks, on the differentiation step? Or any of the other steps, really? Okay, well, we did it. This is a question that can be a real exam 3 style type of a question. Majorly, it's all about doing the logarithm properties. And the last property we have is this one down here. Theorem 7, or this was a numbered theorem. This theorem all alone just says the derivative with respect to x of the natural log of absolute value of x is 1 over x. That's a pretty weird statement when you look at that and really think about it. It's so weird. I think we should really just pause on the problem down below. And let's focus on the statement itself just for a moment. What is going on with that? We do know for certainty that the derivative with respect to x of the natural log of x itself, that one's just 1 over x. But this is saying if you put the absolute value on it, no change whatsoever, still 1 over x. This becomes a very important formula in section 4.6. Chapter 4 is on applications of the derivative, but actually that last section that we cover in chapter 4 is about going from differentiation to integration. And this becomes a really important formula when we try to reverse the differentiation of 1 over x. The answer is going to be natural log x when we start to reverse our results. So let's take a really close look at this and derive the formula. We don't do a lot of derivations in this class, but a derivation is just a good opportunity for us to look into an important formula and also review other formulas that are equally important. This is a good one for that kind of property. The difficulty about this problem is the absolute value of x itself is a weird one to deal with as a derivative. You might have noticed we've kind of just been avoiding it this whole time. We've never differentiated the absolute value of x, but we can. Here's the reason why it's kind of a strange derivative. Its definition comes in two different ways. One classic definition is the piecewise function. Absolute value of x is itself if x is non-negative. I'll express it this way, greater than or equal to 0. And it's equal to negative x if x is negative, and I'll express it this way, saying x less than 0. So that's a definition of the absolute value of x. Another definition is that absolute value of x is equal to square root of x squared. This is kind of a surprising definition in a lot of ways. And in our derivation, we could use one or the other. I think this one is harder. So let's focus on deriving the derivative by using this one on the left. I think it does make a lot more sense. If you're curious on how to do it through this way, just let me know. I'll be happy to run through it. We should also say, what are we trying to achieve with this kind of formula? The ordinary natural logarithm looks like this. It has a domain that goes from 0 to infinity, excluding 0. But if you go natural log absolute value of x in a way that Desmos would understand, there we go. We've essentially doubled the domain. Now you can put anything inside the natural log of absolute value x, except x equals 0 still, because we can now take the absolute value, plug it back into the function, get a result. So we've extended the domain really majorly in this kind of way by including that. And it says, even if it were looking at the restricted domain, ordinary natural log x, the derivatives are the same, just 1 over x either way. Kind of confusing, so that's why we're looking into this a little bit more. So that's the definition of the absolute value of x. And it means if we're going to look into the natural log of absolute value of x, it would be defined in this way. It's the natural log of x if x is non-negative, greater than or equal to 0. That's the natural log of negative x if x is negative, less than 0. So that's how Desmos is getting this graph. If there's an absolute value there, and you throw in natural log of, say, absolute value of -5, you get this result out. But really what you're taking is natural log, put an extra negative there. You're getting the same result. So that extra negative that pops out, if x is -5, forces this into positive, giving you the same function value. So that's what absolute value is allowing us to do, doubling our domain. We're getting the same inputs. So at -5, we're about that high, 1.61. Over here, we're about that high, again, about 1.61. Looks like I hit 5 exactly on that one. But now that we have this, that's something we can differentiate. We're going to differentiate it, and our hope of hopes is we get 1 over x on both branches of the function, no matter if x is non-negative or actually negative. So here's our step where we're going to take the derivative with respect to x of the natural log of the absolute value of x. On a piecewise function, if you're differentiating it, you just differentiate each line. So let's make that thought a little bit clearer by taking one additional step and saying, differentiate with respect to x, natural log of x, if x is non-negative, but differentiate with respect to x, the natural log of negative x, if x is negative. Okay, we're ready to go on the next row or next line. On row 1, this is the nice derivative. Really, it's the same one we cited up here just for reference, differentiating an ordinary logarithm. This gives us a 1 over x, so we'll say the output is 1 over x if x is non-negative. So we've matched up one part of that. If I don't get 1 over x down here, the whole problem is a lie. So this is where we need to be really, really careful, right? Let's look into that derivative. It's a big problem in its own right. So let's maybe separate it out down here. For differentiating with respect to x of natural log negative x, what makes it a bigger problem than the one above is that it's a chain rule, right? It's not x inside, it's negative x. But properties of logarithms can cover this kind of situation a little bit better as well, or will it? Not necessarily. What I was about to say is maybe we could write, I'm going to use a slightly different tool because this is wrong. Red conveys that well. I was thinking of writing negative x. This is well defined because x is negative, right? That's a positive number. And I was thinking rewrite it as negative natural log or natural log negative 1 plus natural log of x, because that's allowed. That's negative 1 times x, except that's undefined right there. You can't just put negative 1 in that position. Desmos will support us on this. Let's see what Desmos says. Natural log negative 1, totally and absolutely undefined. You need the absolute value inside there to make that work, or a condition x less than 0 to force the number positive. So we can't even use properties of logarithms on that thing. Let's back off on that thought. But we can still use the chain rule. So that's what we must do. And the chain rule setup of this one, negative x is the inner function. Natural log x is the outer function. So differentiate natural log negative x, you'll get 1 over something times the derivative of something. Inner function goes in both of those placeholders, down here and down here. And on this fraction, we can just rewrite it as 1 over negative x. From right here, the derivative of negative x is a negative 1. That means we have double negation. This is a positive 1 over x altogether. So coming back down here, it says the derivative with respect to x of natural log negative x is 1 over x. If x is negative as well, again, that's a pretty big surprise. It was only because of the chain rule that this worked out. And we were restricted to only using the chain rule because of domain considerations. But at the end of the day, with this derivation, we have shown the derivative of the derivative of the logarithm of the absolute value of x is just 1 over x. The absolute value bars themselves are just totally annihilated. Weird process, but gives us one new extra tool to work with, which will come back in section 4.6, justifying why we spent so much time on this one. Any questions at all, folks, with running through the derivation? I think the part down here in orange is the trickier part. Okay, well, let's go off now to a problem that we just threw down below here, where we give this new property a try. This is the last problem in the notes. I didn't have any fancy application at the very bottom. My thought was section 3.7 is just a small additional topic in chapter 3, which is properties of derivatives themselves. So let's finish off this next problem, and then we'll take an initial early look into section 4.1 before going on break. So it says, let y be this function, natural log of an absolute value, third degree polynomial, kind of a weird thing. But this property tells us that you can think of this whole problem as not having the absolute values. We don't delete the absolute values because they're required to make this function correct. If you took them out, you'd mess up, well, I should say mess up. You would shrink the domain by a great deal. We took out absolute values, thereby changing the function. So we'll leave them in. We want to calculate this thing. This is kind of a reminder of just what that structure is. dy dx says do the derivative. So that's our first step. Then evaluation bar at x equals 2 just says plug 2 into whatever this result is. It's kind of like a tangent line problem, but we're stopping at getting the slope, not doing anything further. Maybe before we just jump into the derivative, let's do this analysis right here. That part is an inner function. Natural log is an outer function. But notice what I've kind of glossed over. There's actually three functions here. There's the outermost function, natural log. There's the intermediate middle function, absolute value of x. And then there's the actual inner function, the cubic polynomial. Reason I did put in three different derivatives to analyze is because this property takes what's three functions in a chain rule and collapses it to really just two. Absolute value vanishes. So that's spectacular because this could be a hard problem with three functions, but it really just boils down to this. If you differentiate a logarithm, whether there's an absolute value there or not, it's the same exact process. You throw something down below, and then you multiply by that something, whatever it is. So the cubic polynomial gets thrown under the bus down here, x cubed plus 4x squared minus 1. It'll go up into the numerator after differentiated, so we're plugging it here as a reminder. Where the critical thing, easy to forget, is that prime symbol is a great thing to not forget to put on paper because it directs your mind on what's the next step. Down below, just a full-on copy, x cubed plus 4x squared minus 1. Up above, when we take the derivative, we're also multiplying it into the numerator. It's just a 1 there, so we can correctly say 3x squared plus 8x times 1 is just that whole thing. So we've got it, folks. That's the whole derivative. And it's weird, right? It's a complicated looking thing with three actual functions. But this property is, in essence, telling us you can ignore the absolute value as you differentiate. Last thing we'll do is do the evaluation when x is 2. Although you don't have to write this, let's put it on the notes because it's a really strong reminder of what this even is. It's a derivative, which means at any x value inside this domain, we're specifying the slope of the tangent line to that equation. So once we get a value, we'll have an opportunity to see, is it even correct? Let's see that by just putting this on my graph. This is natural log, absolute value, x cubed, 4x squared, minus 1. Notice that there are apparently several discontinuities here. That's because if this is a degree 3 polynomial function, there's at most 3 locations where it would go to 0, causing the natural log to be undefined. So it looks like 1, 2, 3 vertical asymptotes. But what we're concerned about is, what is the slope when you're at 2? Okay, let's take a look. Here we are at 2. This is not telling us the slope, but what it is telling us is the slope of that tangent line, if we drew it, is positive. We better expect a positive number, not close to 0 or anything like that, because then it would be more flat. Out here, the derivative is really close to 0. Looks like out here it might be exactly 0, where it is completely flat for a horizontal tangent line. So with that extra view, we can compute with a little bit of extra confidence, numerical evidence, we have a correct answer. Go dy dx, that's this right here. Evaluate when x equals 2 just means go at the red dot, plug in a 2 for x. 3 by 2 squared plus 8 by 2 in the numerator. 2 cubed plus 4 by 2 squared minus 1 in the denominator. Now let's do the arithmetic here. This is 3 by 4, so 12, plus 16 in the numerator. This is 8 plus 16 minus 1. That sounds like a 23. Let me know if my numbers went backwards on me. So altogether, this is 28 23rds. It is bigger than 1, and that seems about right, because if it was exactly, say, 0, it should have been horizontal as a tangent line here. Something slightly bigger than 1, right at that spot, we drew in the tangent line. Looks like that would be a very acceptable, right in the right ballpark kind of an answer. At that point, unless I made some weird mistake that I hadn't caught, let me know if I did. That would give me an excellent evidence we have the right value. Well, that's the end of the notes. This was kind of an intense section, only 3 examples. But the derivatives were tricky, mainly because of the chain rule, the product rule, and the quotient rule, all just looking slightly different when you throw in a logarithm. But any last questions at all, folks, with the conclusion of these notes? Okay, well, I'm looking at the clock. We have a good, let's see, 25 minutes left. The next section I want to get into is this one, applications of the derivative. But in view of the time that we have and the fact that next week is spring break, how about we just say what we're about to do and call it a day a little bit early? Is that all right with folks? Okay, that way we won't have to do as much refresh when we come back from spring break. It might be a good timing to just start chapter 4 fresh. So here's what's going on in chapter 4. We're now doing applications of the derivative. But what's weird is, sure, it's applications of the derivative, but the main applications are in section 4.4. We need to learn a couple of methods before we get into those main problems. And the major method we're getting into is this one down below right here. The closed interval method, its whole purpose is to find the absolute maximum of the function and the absolute minimum of the function as well. It tells us we need to find the critical numbers of the function. And to do that, really all we need to calculate is, for a critical number, f prime of x equals 0 implies x is a critical number. This is what chapter 4 is all about. Let's pause right here and make this really the last thought for the day. What is this saying? If f prime of x equals 0, it's kind of like what we were saying right here. This is a y prime at x, and it came out as 28/23, which meant the curve is increasing at that point. The slope is positive. But when we're trying to find an absolute maximum or absolute minimum, we don't want a positive slope. We don't want a negative slope. We want a 0 slope. And here's the reason. That's not the reason. The reason is at a 0 slope, that's going to be, say, like right here on this problem. Whatever that number is, let's just call it x. We have f prime of x is 0. Just that equation alone implies a horizontal tangent line. And at that horizontal tangent line, we have a local maximum right here. It's local because we have to really restrict our view to right here to see it as a maximum. But that's where a maximum occurs. And really, that's kind of the punchline to all of this. We are really very interested when a derivative comes out as 0. So we're going to start doing a lot of extra algebra after we calculate the derivative to simplify it as much as possible to actually solve the equation so we can find the values on the horizontal axis that correspond to the 0 derivative. Because this is a lot of thoughts, that's going to lead to the absolute maximums or minimums, or like in this case, the local maximums, local minimums. So that's what chapter 4 is all about. Use our methods in chapter 3 to take that derivative and then solve an equation. But any questions at all, folks, about those thoughts so far? Okay, this is a really early look into what we're going to be getting into. We'll start these problems in earnest when we come back on, geez, that's going to be a while, April 1st. So that'll be our first day back from the break. Well, we'll end class here, definitely a little bit earlier, but I think we all earned it. Thanks for your hard work, folks. And if you have to work more on the weekend, first of all, I'm sorry, but don't hesitate to reach out. I'll be happy to help. Have a great break, everyone. Yep, take care.